Hi, this is Professor Gutierrez. Today we shall be finishing up Chapter 4 of Probabilities, which involves counting. So, for probabilities, this will involve counting. That seems easy enough. 1, 2, 3, 4, 5. Sometimes this can get very, very difficult, though, especially if you have certain things that keep changing. All right, and we're going to talk about that. We're going to talk about combination, permutations, and we're going to talk about arrangements. We're going to talk about all of that fun stuff. So here we go. A lot of stuff on Chapter 4 here. When I'm done, I will upload both this video and this file if you want to take a look at it. It has bookmarks, but that's not, well, it's pretty straightforward. All right. And I messed up by creating a bookmark under a bookmark that should not be there. But, I don't care. Alright, so counting, first off. So we're going to have a lot of formulas, and I'll explain how we get one of them. And the others will simply have to take with a grain of salt. They certainly can be explained, and if you want me to, I can explain them to you. But for right now, we shall just take them as they are. Alright, so multiple counting rule. If we have a sequence of events, first event could occur in n ways, second event could occur in n 2 ways, third event could occur in n sub 3 ways, and so on. The total number of outcomes is simply going to be the product of all of those outcomes. So n equals n1 times n2 times n3, so on and so forth. So one of the examples that I came up with was the Whopper. They used to have it your way right away, and they talk about 256 different ways that you could have the burger. And I have no doubt that there were easily 256 ways. But in their commercial, they said 2 all-beef patties, special sauce, lettuce, cheese, pickles, onions on a sesame seed bun. All right, so we have 2 all-beef patties. So we could either have 2 all-beef patties, or we could say, well, we just want 1. So that is where our first choice comes in. We could potentially have 0, and that would be 3. But it's not much of a burger if you don't have, well, a burger patty there. Alright, next, special sauce. Special sauce sounds kind of scary. So we might say no to the special sauce. So special sauce or no special sauce. Again, 2. Lettuce or no lettuce. Cheese or no cheese. Pickles or no pickles. Of course you want pickles. Pickles are awesome. And onions or no onions. Now, this gives us 2, 4, 8, 16, 32, 64 different ways in which we could have the Whopper. Note also that 64, 128, 256, we're just 4 away from having that. And 4 is simply 2 other choices. Do you want ketchup on that? Yes or no? Do you want mustard on that? Yes or no? 256 different kinds of Whoppers, just from those choices. And so if you were going to guess exactly how someone had their Whopper, you probably could not do it. Truth be told, most people don't care. They just say, give me a Whopper, they eat it, and it's done. You can put mustard in it, special sauce in it, extra cheese. I like extra cheese. But these are different ways of counting. All of these had 2. They didn't have to. And another example is if I get dressed, I could wear a blue shirt, red shirt, or green shirt. Let's say I have 7 different colored shirts. I have 2 different pants that I could wear. And I have 2 pairs of socks. So that's 2 times 2 times 7, which is 4 times 7, which is 28. So that'd be 28 different ways that I could get dressed. I do happen to have 7 different colored dress shirts, which is very nice. I have black pants only, black socks only, and black shoes only. So not too much selection there. I have glasses, which have black frames, and a black jacket. So I have colors in my shirts. That's about where I got it. But anything like that, you can use this multiplication rule to get it. And these are just the lectures that we have up. So An example that they give is when making random guesses for an unknown 4-digit passcode, each digit can be 0 to 9. What is the total number of different possible passcodes? So we have 4 possible digits, and each one could be one of 10. So that means we're going to have 10 for the possibilities for the first, 10 for the second, 10 for the third, 10 for the fourth. 10 times 10 times 10 times 10 is 10,000. So 10,000 different possible codes. And they just do that directly here. 10 times 10 times 10 times 10. So that's 10 codes. Now notice that if we had k positions, so instead of just 4, we had k positions, then the number of total possibilities, n, would be little n, the number that each digit could be 10 to the k. In this case, it's 10 to the 4th. But if we had 1,000 digits, that would be 10 to the 1,000. And so it grows very rapidly, the number of different ways that we could have it. But it's going to be n to the k. Again, that is, we have them in a certain order. We care about the order, but we can repeat. The total number we have there is n to the k. So this would be good for passcodes. This could also work for some license plates. Although license plates are generally 3 letters and then 3 numbers. Telephone numbers would not be this way. No, sorry. Telephone numbers would be this way. Or at least ideally. There are obviously certain combinations you can't have. You don't have the area code 911, for example. And if someone gives you a phone number that starts with 555, they're probably trying to get rid of you. So if we have 10,000 possibilities for this particular code, and we choose one at random, then chances are 1 out of 10,000, or 0.00, or a probability of 0.0001. Or if you multiply that by 100, that'll be 0.01%. So a very small percent chance that we are going to get that. All right, now to look at some of the other stuff, we're going to have to start with the idea of factorials. Now, factorials can be defined for all real numbers and most complex numbers. But since we're not really dealing too much with that, let's just start with a basic definition. A factorial is equal to, let's say, n factorial. And that just looks like a very excited n, like n. No, we don't read it that way. You can read it that way if you want, but okay, so n factorial is equal to n times n minus 1 times n minus 2, all the way down to 1. So 3 factorial would be 3 times 2 times 1, which is just 6. Or 5 factorial would be 5 times 4 times 3 times 2 times 1, which is 120. Now we do have one special case here. 0 factorial is defined as 1. So if you ever have 0 factorial, it is equal to 1. All right. So this would be if we had arrangements that we were making where the order mattered, but we could not repeat. So if we had an arrangement of n items, and we took all n of them and arranged all n of them, then n factorial would be the number of different arrangements that we could have. So factorial, yay! 0 factorial equal 1. All right. So if we wanted to travel, so you were a traveler and you're selling stuff, or maybe you're not, maybe you're visiting, and you want to go to Gallup, Nielsen, Harris, Pooh, Zogby. I have no idea why you'd want to go there. You have a very boring life. But if that is what you want to do, you got the money, no one can stop you. So that's 1, 2, 3, 4, 5 different places. How many itineraries could you have? Well, you could go to any of the 5 to start with. Then the next one, well, you're not going to go back to the same one. You're not going to go to Gallup and say, I really like Gallup, I'm going back. No, you're not going to do that. You're going to go to Gallup, then Pew, then Harrison, then Nelson's, and Zogby. Or you might go Zogby, Nelson, Harris, Pew, and save the awesome Gallup for last. But how many different ways? First choice, you can go to any of the 5. Next, you can go to 4 of the 5, because there's only 4 left. After that, you can go to any 3 of the 5, because you've already gone to 2. After that, you got 2 places left, any of the 2, and then the last one is set. So that is 5 factorial. There's a number of ways you can go. 5 factorial, we already measured that, and that is equal to 120. Boom. So 100 different travel itineraries. Some might be better than others. Probably the cheaper one, or the one that has the least travel. So again, if the itinerary were chosen at random, there would be a 100 in 120 probability of you choosing the right itinerary. All right, now we're going to talk about permutations. Permutations are how many different ways we can arrange something. So if we got 3 things, and we want to arrange them by 3, it's going to be 3 times 2 times 1. Got that. If we have 5 different things we can arrange in 5 different orders, it can be 5 times 4 times 3 times 2 times 1. We just went over that. But what if I have 5 things and I only want to arrange 3 of them? Then it's 5 times 4 times 3. It's no longer times 2 times 1. If I arrange 2 of them, it's 5 times 4. So now we want to look at how will permutations look if we do not use all of them. We also have combinations. Combinations just means we have a group. We don't care what the order is. And we're going to look at both permutations and combinations. We got them right over here. I'm going to bring this down. All right. So, permutations, positions, committees, combinations. If that helps you know it, great. Yeah, makes sense. All right, permutation rule. If we have n different items available for our different slots, we can select them without replacing. With replacing, it's just n to the k. Or in this case, it would be n to the r. However, selected without replacement, the probability n, choose r, is equal to n factorial over n minus r factorial. So if we had 10 items, and we want to say I had a class of 10 and I wanted to pick the first 3 students for something, I don't know, to go out the door, to come see me after class, anything, but the order mattered. In that case, I would have 10 factorial over 10 minus 3 factorial. Now that seems kind of big, or at least it seems kind of cumbersome, because if I have 3 students, the first choice could go to any of the 10, the second choice could go to any of the 9 remaining, and the third choice could go to any of the 8. And that's what I had here. I had 10 students first, then 9, then 8. So first 3 students out of 10, I can choose 10 times 9 times 8, which is equal to 10 times 9 times 8 times 7 factorial over 7 factorial. I can multiply by 7 factorial over 7 factorial. That's 1. That's perfectly fine. 7 factorial times 8 is 8 factorial. 8 factorial times 9 is 9 factorial. 9 factorial times 10 is 10 factorial. So on the top here is just 10 factorial. So 10 factorial over 7 factorial. That is equal to 10 factorial over 10 minus 3 factorial. Again, it seems very cumbersome, but it will become important later on, and we'll see why. All right. So trifecta, a lot of probabilities have gambling benefits. All right, in a horse race, a trifecta is won by correctly selecting the horses that finish first, second, and third, and you must select them in the correct order. The 140th running Kentucky Derby had 19 horses. assuming there's a question here. How many different trifecta bets are possible? If randomly selected 3 of those horses for a trifecta bet, what is the probability of winning selecting California Chrome to win, Commanding Curve to finish second, and Danza to finish third? I am just going to assume those are horse names. I hope. As they did. Oh, okay, apparently they did. So how many different? So it's going to be 1 out of, and then whatever this probability, or whatever this permutation is. So we have 14 horses, and we choose 3. So that's going to be 19. Forgive me. We have 19 horses, and we choose 3. So 19 choose 3. 19 factorial over 19 minus 3 factorial is 58, 14. So you had a probability of 1 out of 5,800 of getting the correct trifecta. Most people will not bet the trifecta randomly, but if you were to do so, then you could do it. All right. So this is showing us that without repeating. And that is my soda. I like soda. And so for 10, I did it this way, and then I show how it works here for in general. $2 trifecta bet would win 34.24.60. So if you get the right trifecta, you will win. However, notice that the odds of that happening is 1 in 6,000. Probably not going to do any good. On the other hand, $2 will buy a soda outside of class. Not a card, because cards don't work in those machines. But, yeah. All right, permutation rules when we have multiple items that are together. This one is not too terribly important, but certainly can have its uses. N factorial over n minus 1 factorial, n minus 2 factorial. Let me give a quick example here. And if you want, you can go over it. I'm going to go ahead and skip it for now. So we can get to the combination rules. All right. So combination rules are for we have certain items available. We choose R of them without replacement. And this is the number of different combinations that we have. Note that order doesn't matter here. This could be used for poker, or this could also be used for blackjack, where it doesn't matter what order you get the cards in. If you have a situation like that, you have n factorial over n minus r factorial over r factorial. Notice that this is just permutations divided by r factorial. In other words, it's just it's dividing the number of ways that you could permute the permutation that you have. The permutation that you have? Yes. I'm going to stick by that statement. All right. Again, gambling. Why did I do this? In California, 5 lottery game. Winning the jackpot requires you to select 5 numbers, 1 to 39. You do not care what number those orders come in. All right. The same 5 numbers must be drawn in the lottery. The winning numbers can be drawn in the order. How many different lottery tickets are possible? No replacement, so you're not going to choose the same number. You have 39, choose 5. And that's how you read that. 39, choose 5. Or probability of winning the jackpot when 1 ticket is purchased is 1 divided by how many different lottery tickets are possible. Assuming that not even assuming somebody wins, just in general. So 39 choose 5 is 39 over all that. Plug it into a calculator, we can get it. Now there's some calculators that have a probability or a statics mode, which can show you combinations, permutations, and the like. And you can just put in what n is and put in what r is. All right, so chances of winning that lottery are 1 out of 575,000. This is one of the reasons I do not play the lottery, because it is a tax on people who are bad at math. But we're not bad at math. We're good at math. All right, and the last one is probability through simulations, and we just go here and we get some simulations. That's it. I will actually go ahead and show this website. I'm not going to download anything because this recording is getting a little long. And we'll just let it contact server. Let it do its thing. No, we won't. See, I cancel and it counts. That happened last time and it happened this time. So that's pretty good. Click on this book. Download data sets, view and download textbook supplements, access technology download, and view instructional videos. So we have all of that we can play with if we would like to. That is what we have for now. I will see you in the next video. Bye-bye.